This is still chapter 8, talking about internal flow. This is lecture 9. The previous lecture, I solved an example of the first type where you have to find the pressure drop or the head loss once the other factors are given. Here I want to solve another example of another type. So I am still in the turbulent flow in pipes. And when you go through your book, you will see that there are other examples. I'm here just mentioning two of them, determining the diameter of an air duct and determining the flow rate of air in a duct. So I will keep this for you, and I'm going to discuss this example here. So this is the example, determining the diameter of an air duct. So what do we have here? We have heated air at 1 atmosphere. So you are given the temperature, you are given the fluid, which is air, and 35 degrees centigrade, and you are given the temperature. So given the pressure, the temperature, the fluid, so you need all of those things to get the properties, the density and viscosity, etc. So heated air at 1 atmosphere and 35 degrees centigrade is to be transported in a 150 meter long circular plastic duct. So again, you are given the length here, and for the first time you are given a plastic duct. Plastic duct means this is smooth pipe, and epsilon is equal to 0. Okay, so epsilon over d is equal to 0. So in the Moody chart, you use the line which is at the bottom. At a rate of 0.35 meter cube per second. This is the volumetric flow rate. If the head loss in the pipe is not to exceed 20 meters, so now HL is given, not to exceed 20 meters, so this is the specification of HL. Determine the minimum diameter of the duct, and he's asking for the diameter, so this is a problem of the third type. Okay, this is a problem of the third type. So how to solve it? So first of all, if we want to think about the assumptions, as usual, the flow is steady and incompressible, the entrance effects are negligible, and the flow is fully developed. You have to mention those always. The duct involves no components such as bends, valves, connectors. You want to make sure that this is purely a straight pipe without other let us say components. Number 4, air is an ideal gas, so that I can use, if I want BV equals nRT, or I can use the tables since this is at 1 atmosphere. And the duct is smooth since it is made of plastic, as I said, so this is epsilon equal to 0. And finally, the flow is turbulent and to be verified. So I will assume that the flow is turbulent because, as we said many times, most of the flows are turbulent. So I will start by this assumption. Why I am assuming it? Because I don't have the diameter, so I cannot calculate the Reynolds number, so I cannot decide from the beginning. So I will assume it is turbulent, and then I will continue with that assumption. Okay, so I know that the temperature is 35 degrees centigrade. I have 1 atmospheric pressure, so the density is 1.145 kilogram per meter cube, and then for the dynamic viscosity is such, and for the kinematic viscosity, if it is needed, this much. So the properties are given here. You can read them from the table. The density, dynamic viscosity, kinematic viscosity can all be obtained from the table. Okay, this is important. This is the analysis. Let me go through the analysis with you. So this is a problem of the third type, since it involves the determination of a diameter of specified flow rate and head loss. So we said this is the problem of the third type because I want to determine the diameter. Now he's proposing 3 approaches to solve this problem. So we can solve this problem by 3 different approaches. The first approach is the one that I talked about it before, which is an iterative approach by assuming a pipe diameter, calculating the head loss, comparing the result to the specified head loss, and repeating the calculation until the calculated head loss matches matches the specified value. So this is the first approach that I discussed before. The second approach is where you write all the relevant equations and you leave the diameter as your unknown. And then you solve those equations together using an equation solver. And this is the approach which the book used. And then the third approach is just to jump to Swami and Jain formula and see what we will get. So the book uses the last two approaches, so you can try this, the iterative approach. So you can try this iterative approach by yourself, and we'll talk about the other two approaches. Okay, so to list all the equations, we are just going to list all the equations we have. So for example, the equation for the velocity is equal volumetric flow rate over area. And as you can see, here I have the diameter and the velocity to be two unknowns. Then the Reynolds number is equal to Vd over kinematic viscosity. And here is V is unknown, D is unknown, and the kinematic velocity is known. And then in this equation, as you can see, this is the friction factor equation. And I have, just because epsilon over d, epsilon is equal to 0, so it reduces to this one. And again, I have what I have, R, E, and F here. And finally, HL is known, and F is unknown, and D and V are the unknowns. So how many unknowns I have? I have V is one unknown, D is another unknown, RE is unknown, F is unknown, and I believe that's it. Okay, I believe that's it. So V, D, R, E, and F, and I have four equations. So I have four equations, four unknowns, and you can solve those equations using the software, for example, MATLAB or Excel, use GoldSeek, etc. Any approach can be used to solve those equations. So so the roughness is approximately equal to 0. Therefore, this is a set of four equations and four unknowns, as I have just said. And here we use a software called Qais. The book used this software, and using this software, the diameter obtained to be 0.267 meters. The friction factor was obtained, the velocity was obtained, and the Reynolds number was obtained also to be 100,800, which means that note that Reynolds number greater than 4,000, so the flow was found to be turbulent, and the assumption was verified. So the diameter, which was let us say the thing that we are looking after, was found to be 26.7 centimeters, and this is using this approach. Now the diameter was also determined from the third Swami and Jain equation or formula, and by direct substitution, the diameter was obtained to be 0.271 meter, which is 27.1 centimeters, which is a great match by Swami and Jain. So as you can see the discussion, note that the difference between the two results is less than 2%. Therefore, the simple Swami-Jain relation can be used with confidence. Finally, the iterative approach requires an initial guess of D. If we use the Swami and Jain result as our initial guess, the diameter converges in a short order. As I said that, so there are these three approaches. The first approach is the trial and error, but instead of starting from nowhere, you can start with Swami and Jain. Swami and Jain will give you this as your D1, and then use it in your the iterative approach, so that hopefully you will convert fast using the Colebrook equation. Or you can have all the equation written and solved together, and then hopefully also you will get the correct answer. So this is an example of the third type, and there are two other examples in the book, so you can practice more in addition to the recommended problems.